In this video, we solve problem 14.6.008 from the Larson and Edwards Calculus Early Transcendental Functions textbook 7th edition. We're asked to evaluate the iterated integral. It's actually pretty simple. You just start with the innermost integral and you work your way out. Now, an important thing to remember is that the innermost bounds go with the innermost variable. And that second set of bounds goes with that second variable here, and that third set of bounds goes with the third variable. So we're going to focus on this. We're going to leave this alone and leave this alone for right now, and then we'll anti-differentiate with respect to y. Now, natural log of z doesn't have a y in it, so that's constant with respect to y. The antiderivative of a constant with respect to y is that constant times y. Just to make this unambiguous, I'm going to put the y in front of the log. So I've got y times natural log of z, and I'm evaluating this expression from y equals this value to y equals that value. It's not too bad. You just anti-differentiate and apply the fundamental theorem. Just remember that these bounds are values for y. Don't substitute them for z or anything else. Okay, so I replace y with 1 over x times z. And I replace y with 0, but that gives me 0, and then I subtract. So I have this minus 0, which is just itself. And we're done with that part. And then we do the next integral. This time we're integrating with respect to z. So the 1 over x is a constant this time. Just to make everything look a little bit simpler, I'm going to factor out that 1 over x. And now I'm here. Then I focus on this integral and I evaluate this. Now, if you're unsure of the algebra, let me just remind you, if you have a fraction times a fraction, you just multiply straight across. 1 times 1 is 1, x times z is xz, so this is equal to this times this. Now, another thing you want to be careful about is that you can take this 1 over x out of this integral because there's no x right here. But you cannot take this all the way outside all of the integrals, because we still have to integrate with respect to x. That's a variable with respect to x, so this expression can't go outside this integral, the dx integral. So it just needs to stay right there. It can't go all the way out. Okay, so I want to anti-differentiate this with respect to z. And the first thing I ask myself is, do I have a rule for that? And I don't, because it's a product. I've got something times something else. So I'm going to have to do something else. If I don't have a rule for that, I always try u-substitution next. The question becomes, if I choose something to be u, is du a factor somewhere? Or maybe a constant times du, is that a factor somewhere? And yes, that actually works out this time. If I let u equal natural log of z, and I compute du, that's the derivative of this times dz, I get 1 over z dz. Question is that up there? And actually it is. It's up there. It's exactly up there, just as that expression. It's 1 over z times dz right there. So I can write everything here in terms of u, so a u sub is a good approach for this problem. So I want to choose u, then we computed du, and then the next thing we need to do is we need to change our bounds. If these are bounds for a z, we're saying integrate this function from z equals 1 to z equals e squared. When I change to u, I need to integrate from u equals some value to u equals some other value. To find those values, I just substitute these in for z right here. You take the old upper bound, e squared, and you substitute, and that gives you the new upper bound. You take the old lower bound, 1, and you substitute that to get the new lower bound. And then of course we want to simplify these guys using log properties. Remember, natural log and the exponential function are inverse functions. They undo each other. So the natural log of e squared is just 2. You can also say to yourself, well, e to what power is e squared? E to the second power. And the same thing here. This can be simplified. Natural log answers a question. You say e to what power gives me a 1. Whatever goes in that box goes over there. Well, e to the 0 power is 1. That's a 0. Another way you could get this is you could just remember that natural log of 1 equals 0. That's what that graph looks like. When x is 1, y is 0. So we've got new bounds. U goes from 0 to 2, and we're integrating u with respect to u. Everything else is still there, that 1 over x, the integral from 1 to 7. And the dx over on the far right. Now I want to evaluate this integral in terms of u. So we'll use the power rule. We add 1 to the exponent, divide by the new exponent, evaluate from u equals 0 to u equals 2, and subtract. It's just the fundamental theorem. U squared, if u is 2, u squared is 4, so this is 1/2 times 2 squared, which is 4, minus 0 squared, which is 0. Whoops. And of course, half of 4 is 2. And so you're right here. And the last thing we do is we evaluate this integral with respect to x. We get 2 times the natural log of the absolute value of x. Evaluate from 1 to 7. It's just the fundamental theorem. Oops, here we go. And natural log of 1 is 0. So we get 2 natural log of 7, or you could bring that 2 up inside the logarithm as an exponent, and that'd be natural log of 7 squared, or 49. Either one of those is fine. So let's review what we did. You start on the innermost integral, and you integrate with respect to y. Then you replace y with this, and you apply the fundamental theorem. Then you go to the next integral. Now you're integrating with respect to z. So we anti-differentiate with respect to z, and it turns out we need a u substitution for that. So we choose u, we compute du, we find new bounds, then we write the integral in terms of u, then of course we anti-differentiate with respect to u, and then we use the fundamental theorem again. And then the last thing we do is we evaluate this integral with respect to x. So we anti-differentiate with respect to x. We use the fundamental theorem, f of 7 minus f of 1, and then we simplify. Easy breezy.